So we're happy to have with us today Ido Greenberg from the Technion from NVIDIA, who will come and tell us a little bit about sort of a summary of some of his important works in reinforcement learning. Thank you, Ido.
Hi everyone, and thank you Moshe for the invitation. So my name is Ido. I'm just finishing my PhD in the Technion, and I'm starting in NVIDIA as a senior research scientist. And today I'm going to talk about selected works from my PhD. These works are somewhat here and there, and they're like in different topics. So I already see it made some difficult life for one of you who had to cover the background for them. But if I try to draw a common line between these works, I think it's about taking learning and adjusting it to the conditions in the real world. So I'll start with a brief overview. I started here in the Hebrew University in Talpiot program, so it's always special to come here. And we can skip directly to the right part, to my PhD, which focused on reinforcement learning, and more specifically on taking the pretty amazing achievements that we have in the literature of reinforcement learning and making them more applicable to real-world problems. So we have the issue of performance awareness, where sometimes in real life things don't happen as we expected, and we want to notice that something is unusual before things get too bad, before the car drives off the cliff. And also, if we're able to, we would like to prevent the bad things from happening in the first place by learning a risk-averse policy. So this is going to be the focus of the first part of today. Also had a couple of works about other topics. One of them is the Kalman filter one, which we will discuss in the second part. And I also had internships at Google and NVIDIA. In Google, we tried to make Google Assistant more engaging for the users using reinforcement learning. And in NVIDIA, we tried to improve solutions for the traveling salesman problem in order to accelerate deliveries and stuff like that. So we are going to focus on these two parts. And let's dive into the first one, risk aversion. So I guess most of you are already familiar with reinforcement learning, but even if you're not, don't worry. All you need to know for this talk is that in reinforcement learning, we have different episodes. Every episode is like a game or a scene or a drive of the car. And every episode we need to make a decision after a decision after a decision. Each time we observe the environment, we make a decision, we get a reward. At the end of the episode, we count all the rewards. And this is the total return, and this is what we want to optimize. Okay, so this is reinforcement learning. And we want to focus on risk-averse reinforcement learning, and I think the motivation is pretty clear. Like many real-world applications are risk-averse by nature, like driving and medicine and finance, and even other applications that are not explicitly risk-averse. We usually have like uncertainties that we don't know the dynamics exactly, or the train environment is not exactly the same like the test environment. So we want to be robust to these changes, and it can be shown that for certain types of robustness, this task is mathematically equivalent to risk aversion. So for all these reasons, even in applications that are not risk-averse, we would like to be able to do risk-averse reinforcement learning. Now the next question is why we actually need a dedicated framework for this problem. Because if we don't want the car to bump into a wall, we can just say that bumping into a wall is worth like minus gazillion points, and then we can just optimize the expected return like everyone else. And this is sometimes valid, but it also has several problems, this approach. First of all, what exactly is minus gazillion? Is it like minus 10 or minus 1000? And even if we know how to set it, if it's very extremely low, then essentially all the other rewards are about the same, so we effectively have kind of a sparse problem. We can only learn to avoid the risk and nothing else. And if you're still not convinced by that, then you can actually construct an MDP, a reinforcement learning problem, where the being risk averse cannot be expressed by reshaping the rewards like that. Like it's mathematically impossible. So for all these reasons, we actually do need a dedicated framework for risk averse reinforcement learning. And one such a common framework is to replace the objective. Now instead of optimizing the expected return, we want to optimize some risk measure of the return. And one common risk measure is the CVAR, the conditional value at risk. If this is the distribution of the returns over episodes, then this is the average of the distribution. And we are going to focus on the tail of the distribution, on the worst alpha quantiles, and take the average over these worst alpha quantiles. This is the CVAR risk measure. So it is a coherent risk measure, which means that it satisfies certain desired properties, and it is commonly used both in applications like banking regulation and also in the literature, including reinforcement learning literature. So that's what we want to optimize, and now the only remaining question is how we are going to do this.
Technical question?
Sure.
Since we are estimating it empirically, and now the T different experiments are not independent anymore because you used all other experiments to determine which are the alpha worst ones. So we don't run into statistical problems that you need to have some.
I mean, we collect, it's in the next slide, we're going to be collecting like each time 100 episodes, let's say, and the episodes are IID. And then usually what we do in policy gradient, which is the, okay, I'll just finish the slide and get to it, and if it's not clear, ask me again. So how are we going to, yeah?
Additional question for the previous slide. Well, we show here a Gaussian of the data, which is very meaningful, but how can you...
This is just an illustration.
Just illustration,
figure.
okay.
I mean, I don't assume it's Gaussian. I don't assume I know anything. This is just to explain what the CVAR is. I mean, usually we just look for the expectation, and now we look at we want to optimize the tail. Okay, and the way we're going to do that, well, generally in reinforcement learning, the most common approach is policy gradient, and all the actor critics are variants of that. And essentially what we do in that approach, if we zoom out, is we have a policy, we run it for like 100 episodes, and we take the data from these episodes, and we feed it into some optimizer. The optimizer is, it uses some equation of the policy gradient in whichever variant, it's not important, and then we take the updated policy and we feed it again, we use it again to collect another batch of episodes. So these 100 episodes, we can assume they are IID, and then if we want to optimize the CVAR, then what we are going to do is to add this step in between. And now, every time we collect 100 episodes, we're going to say, okay, we only want to improve the worst 5%, so let's take the worst 5 episodes with the lowest returns and feed only them to the optimizer. And when I present it this way, I think the first problem with this approach is very clear. We essentially throw away most of our data immediately after we collect it. So this is very simple and efficient. By the way, did I answer your question about the IID episodes?
The fact that they're IID, I'm not sure to see how it affects the. So the question is which are the worst, the truly worst. You know, like what is the random variable that is IID? Because like the identity of the ones you chose is affected by everyone else. So in that sense, you know that the experiments are IID, but the random variable that you're estimating.
That's actually a good point. There is some source of biased gradients in policy gradient for the CVAR, which does not exist in policy gradient for the expected return. And this source, it has to do with the fact that what we are supposed to do here is to take all the episodes that are below the alpha quantile of the true distribution, and we don't know the alpha quantile of the true distribution. We just estimate it from the data, And this translates into what I said, which is just taking the worst 5% episodes. But in fact, if the estimator of the quantile is biased, which it often is, then you indeed have statistical problems, but this is like quite minor. There's another bias issue which is more measured, but this is also quite orthogonal to what we are going to discuss here. So thanks for the comment. Yes.
Can you prove or show that that does give you optimal performance on the main task?
What do you mean by optimize? I can show that this algorithm, it gives you the an estimate of the a consistent estimator of the true gradient of the CVAR return. It's not equivalent to optimizing the expected return. It's also just the gradient, so it's still vulnerable.
Yeah, to solve the CVAR problem, how do you take care of the main task? I mean, in the end, you want the
what is the main task?
Yes.
In my motivation, I replaced the objective. I don't guarantee. I certainly don't guarantee that I optimize the expected return, because we said we are now risk averse. We care about the expectation, but we care more about the worst cases. We want to guarantee that we don't have too bad performance on certain drives in the roads or on certain users of our application, and we are willing to give up somewhat on the expectation to do that. Okay. So we have this approach for policy gradient for CVAR, and we see that it's highly sample inefficient, and it also has a second problem, which I'm going to illustrate through this toy benchmark called the guarded maze, where we try to reach the green target as fast as possible. However, if we pass through the red zone, then with a very small probability, we're going to get a very high penalty. So on average, it's still worthwhile to take the short path, and once in a while to get the penalty. On average, it's still the best. It was supposed to be a surprise. What happens if we use the CVAR policy gradient because we are risk averse, we don't want to take the short path, then we would expect it to learn the long path instead, but in fact what's going to happen is that we're going to just learn to do nothing. We just get far away from the risky area, and that's it. And the reason for that is that during training, every time we explore the successful strategy of taking the long path, this is a pretty good episode. So if it's a good episode, it's not one of the worst episodes, so we're not even feeding it into the optimizer, so we're not able to learn it at all. So it's not just that we throw away most of the data, we actually throw away very critical data that we were supposed to use for learning. And if we try to generalize this phenomenon more formally, then we call it blindness to success, and we see that every time we optimize the CVAR, if we have discrete rewards, then the distribution of the returns, if we look at it as a quantile function, like the inverse CBF, this distribution is a step function because the rewards are discrete. And if at any point of time during training, the first step, which is the one worst outcome, if it's wider than alpha, let's say, for example, we learned not to take the short path anymore because it's too risky. So now we have pretty much two different cases. Either we take the long path, and that's quite good, or we just do nothing, and that's bad. And essentially, all the worst alpha quantiles of our experience, they're always going to be in this first step, in this doing nothing, and then there is no differentiation at all between the episodes in the data. So the algorithm is not able to tell what's better and what's worse, and this means that we have zero gradient. The gradient of the CVAR return is just zero, and this is a local optimum, which is also very difficult to escape. And this is the second problem that we face. Yeah.
For this specific story example, I assume like a naive trick, which is like adding lambda for a very small lambda times the expected loss will already get to solve the problem, right? Because so, I would change the optimization such that it's going to be CVAR plus like a epsilon times the expected reward. That will probably solve
So
it.
if you change
it's a technical trick, or they're more complicated.
So if you change the objective, then I guess you can overcome the problem. But
arbitrarily small epsilon, you basically get the same objective, but still it could hint to go somewhere. So the question is like, did I find a solution for this particular example, or is it?
No, I'm going to do something a bit more general, but and also I guess that if you use a small epsilon, then I guess I can come up with a counterexample that still won't work. And if you use a large epsilon, then you already you have a different objective. So we want to solve these two problems, and the key insight to our approach is that when we take the worst episodes, we do two things. We mix up two different things. One of them is having bad luck, bad conditions, something in the environment happened differently than I hoped to, and the second thing is that we made bad decisions. We didn't take the long path. We made things that are not smart, and then we do want to focus on the hard conditions, but we don't want to ignore all the good strategies, all the good explored decisions that we made. So we have two components in our approach. One of them we call soft risk, which simply says instead of taking just the worst 5% of the episodes, let's take the whole 100%, the whole batch that we sampled, and learn from that, and we will decrease this gradually during the training, and only on the last part of the training we are going to actually focus only on the worst alpha percent until convergence. And this clearly overcomes the blindness problem, because now at least in the beginning we are going to see everything, but naturally it means that at the beginning we are not going to be risk averse. So to remedy that, we are going to also use the cross entropy method in order to notice which conditions of the environment are more difficult and oversample them during training. Okay, so you can think about some latent variables in the environment which affect some of the randomness, and we are able to control. So we understand which values of them are more correspond to more difficult outcomes, and we just oversample them. So if we want a concrete example, in the guarded maze, we could take just the cost of crossing the red zone, and we can notice that high values of this cost correspond to lower returns, so we can just simulate higher values. And in a more realistic scenario, you can think about driving, so these latent variables could be the place and the time of the driving, and we see that driving in the city center or on rush hours is more difficult than other scenarios, so we are just going to focus our training more on these scenarios. Okay, so this is the basic idea, and this allows us to both preserve the risk aversion, even though we have this soft risk, and also, since we now collect the more relevant data, the hard data in advance, then we don't need to throw away most of the data. So this also recover our sample efficiency.
This is equal to moving the sampling distribution in classical important sampling closer to the real distribution.
So the real distribution is what we sample in the first place. This is about sampling not the real distribution, but the difficult parts of the real distribution on which we want to focus. So this is kind of a target distribution that is different from the first one, and indeed we need to use important sampling after we do that in order to fix the sampling issues. Yeah.
And means how do you use them in cross entropy?
So you didn't miss it. I just didn't get into it. I don't think I will have time to get into the details of how the cross entropy method works. Essentially, if you have 100 episodes and you say, okay, now I have the worst 5 episodes out of them. So the next batch of episodes I want to be closer to these 5. So you know the driving hours and the locations in the worst 5 episodes, and then you can try to fit their distribution for the next batch. But fitting only the worst 5%, it's too extreme. It's hard to fit. So instead of that, you fit the worst 30%, and then next time you again fit the next 30% until you converge to the actual extreme tail of the original distribution. That's the main idea. Yeah.
Continuous of the third question here is about
Sorry. So in the previous slide, I went over the policy gradient approach. So the way I presented it is for online reinforcement learning. I mean, we collect batches according to the current policy, and we only learn on these batches. So online.
So this talk is
yes, this talk is only about online. Yes. Okay. So this is our method, and we already understand how it helps us to solve the guarded maze and to learn the long path. We also tested it on several other benchmarks, including this nice driving game where we are the blue car. We follow the red leader. We need to follow it as close as possible, but without actually bumping into it. And we see that when we apply scissor instead of the naive policy gradient, we get very interpretable risk-averse behaviors, such as keeping more distance and using the gas and the brakes less. And as a result, we also get rid of all the car accidents. We are able to, using this approach, to preserve a perfectly safe drive. So I think this is a very nice result, and this is the results we have about reinforcement learning. If we now, I mentioned before that our approach takes a latent variable of the environment that affects randomness, and we need to find this latent variable and control it. And this really calls for the framework of meta-reinforcement learning. In meta-reinforcement learning, we have different tasks. Each task has different dynamics or rewards. So very naturally, we have this latent variable, the task, which affects the randomness, and this really fits our approach. So you can think about training a robot to walk, and but we have each time a different instance of the robot, and it has slightly different friction in the joints, and the flow might be slightly different. And we want usually we want to optimize the expected return over all the tasks altogether. And as you can guess, we are going to propose to modify this task if we want to be risk averse, if we want to be robust to the task. You can think about the tasks being different users, and we want all the users to be reasonably satisfied, and we are willing. We don't want any of them to be angry, and we are willing to give up on the average satisfaction to achieve that. So we could use a CVAR objective. Okay, and notice that here I defined the CVAR objective not as a CVAR over the whole joint distribution of all the randomness. I use CVAR over the tasks, but expected value over the returns within tasks. And we can debate about the applicational motivation, but if we focus on the algorithmic aspects, then defining this decoupled objective is very beneficial, because if we had blindness to success in risk-averse RL, now in our decoupled objective in meta-RL, the way we defined it, we just never have it. We don't need to do all this soft risk and all these tricks, since we focus on the worst tasks, but we are looking at all the episodes within them. We no longer have this blindness to the successful experience within the tasks. And we still have the sample efficiency issue, but we can overcome it using a very similar approach, just learn to sample the low return tasks. And well, I didn't get into it. I actually mentioned it in the beginning, answering your question, that we sometimes have bias in risk-averse enforcement learning when we optimize the CVAR. And this is I didn't get into it because it was quite orthogonal to what I said till now. But it's actually a quite important issue when we optimize the CVAR in reinforcement learning. And we see that in the meta-RL framework, if we define the objective this way, we are just immune to this problem. We have no bias at all. So this is very nice to see that we bypass many of our problems just by defining the objective slightly differently, and this actually connects to what you said about your idea about using an epsilon CVAR approach. So yeah, yeah. Sorry.
If, for example, like all of the episodes, all of the tasks are in the same hardest level,
Okay.
so you will just optimize over regular events, not really bad events.
Yes.
So also in the more general case, you will look at all of the episodes in the easy tasks. So maybe you will still have car accidents, for example, because the fact that you
So if what you essentially say is that if instead of taking the time and the location of the drive, I take the color of the car, and then I choose the hardest colors, and if there are no really harder colors, I just take arbitrary episodes, and then I focus on them. That's what you say?
Yes, but also if you take the hour of the time in the day,
okay,
still the fact that you are not making accidents in the night doesn't imply that you don't make accidents in the morning.
I mean, if you see empirically, I'm not sure I understand the question. If you see empirically that there are more accidents in the morning, we can discuss statistical significance, but eventually, if you see that that's what's happening, then you want to focus on the morning because these are the cases where you do the worst, and you want to improve these worst cases.
The point is, worst case is not objectively, it's with respect to your policy. If you came up with a weird policy where the day you're doing worse in the day relative to the night, so then that will be the one that you'll optimize. I think, like night objectively is harder, but if you came up with a weird policy that causes you to do worse during the day, so then that's what you will be optimizing.
When I say hard, of course, I refer to the outcomes of the agent, the scores, the returns. So if you say that it's harder to drive at night, but you see that the lowest returns are in the day, so in what sense?
I talked about the all episodes, but that's
okay. So we have our approach Rommel, which oversamples the lower returns tasks, and we apply it to several problems again, and we can see that, for example, in this Mojoko problem, in this humanoid problem, we change different things in the environment so that it's a meta problem. We have different tasks, and one of them was the mass of the body of the agent, and we see that our method was able to detect that the mass is a significant variable of the task, and specifically high body masses correspond to worse performance, so it oversampled them, and as a result we have better performance in these worst case tasks, and also we have a more uniform performance over the whole space of tasks. So I think this is quite a motivation that we had, and we see it here, and we also see again an interpretable behavior. I'm not sure I can call it risk averse, but the agent just leans forward so that it doesn't need to lift its heavy legs in order to work. It can just let the gravity pull itself forward. Okay, so this is what we have on risk averse reinforcement learning. Possible future directions are to replace the CVAR because, well, we saw that the CVAR has certain problem with its strictness, and also in terms of motivation, CVAR 5% means that we assign a lot of importance to the fourth quantile and zero importance to the seventh quantile, and this doesn't make a lot of sense. We do want to focus on focus more on the worst quantiles, but not infinitely more. And the second possible direction is, well, we have nowadays the framework of distributional RL, which means that we already learned the whole distribution of outcomes. So this really calls for using it for risk averse or any risk measures of the of the return that we want to optimize. And indeed, there are already works about this topic, but we can see that similar problems to what we discussed today still exist in the distribution RL framework, the blindness to success and stuff like that. So it's interesting to study them there and see how we can overcome them, what other problems we have. So this is about enforcement learning. Do you have any further questions before we move to the second part? Yeah.
As I understand, if you have fixed reward, yeah, like for each state and policy, you have the reward not change during the learning.
The reward might be stochastic, but it doesn't. I mean, the function, the stochastic function of the reward per state action, no, it doesn't change. I mean, it's not a non-stationary problem or something like that. Yeah. All right.
What would you expect if it was a reward function that changes in the episodes?
Non-stationary problems are a whole different framework, and if you do it model-based, then you need to somehow update your model more frequently, but here we deal with a policy gradient, which is usually not model-based. So, I mean, I don't, if you assume that the changes are continuous, and you do online learning anyway, right? We said we don't do offline RL here. We already learned from the most updated returns that, the most updated, up-to-date experience. I don't think you have anything else to do. Practically, you can do more training if we have the collection of data and the update of the model. You can do the updates more thorough in order to forget more about the past and to be more up to date. But I can't think of anything. I don't think this affects directly the models that I mentioned here. All right. So that was about risk-averse reinforcement learning. And the second part is going to be about Kalman filtering. This started as a collaboration with ELTA. And well, you already discussed a bit the Kalman filter. I saw, so this is a really popular method for like 64 years already. And the basic idea is that we have noisy measurements of some dynamic system, and we want to estimate the state of the system. And you already used the example of tracking a car or a plane, and we want to, we have, for example, radar detections, and they are noisy, and we want to know where exactly the plane is right now. So at a certain point of time, we think that it's somewhere around X. We don't know exactly. And then some time passes, and now we have some notion of some model F that tells us how we think the plane has moved. So now we think it's here. And also the uncertainty grew because our prediction of the dynamics is not, the model of the dynamics is not accurate. There is some noise, Q. So the uncertainty grew. And now we get a new measurement, Z, which is, for example, the detection of the radar, which is also uncertain. It has some noise R. And we take this new information and the previous information and we filter them together in order to get the next estimation of where we think the plane is, what's the state of the system. So this is the idea of the Kalman filter. We can do that repeatedly, and if you went through the equations, then they look something like this. This is the prediction step of moving time forward, and this is the update or filtering step. We're taking the two pieces of information together. So this is the Kalman filter, and on inference we have the 7 measurements till now, and we want to tell what's the true state X at time 7 or 8, depending on whether you do a future prediction or just current estimation. That's on inference. On training, we assume that we have, in this specific framework, we assume that we have a data set of trajectories. In the trajectories, we have the observations, the z's, and also we have the x's, the true ground true states of the system. For example, if we run simulations, then we know the true state. If we have controlled experiments for training, then we also can track the true state of the system with a very high accuracy. Maybe we have someone that can manually label the states in some arbitrary data. So in many realistic scenarios, on training only, we do have the ground truth within the data. And then we want to somehow use it in order to train our model for inference. So we have the models, the motion model F, and usually we don't really learn it from data, we just predefine it manually. We'll see in the next slide. And we also have the noise of the system, the noise in the prediction and the noise in the observation. And they're just the covariance matrices of the noise. So once we have this data that includes both the x's and the z's, we can just calculate the sample covariance of the noise in the prediction and observation. So we can just estimate the noise and set the parameters like that from the data. The thing is that this is often not sufficient because the model of the Kalman filter is linear. F is a constant matrix and we multiply it by x, so this is a linear model. And one such common model in tracking, for example, is the constant velocity model. And you know, any deviation from this constant velocity is considered as part of the noise. But if we have some targets that we track, and now it deviates to the left, and now it deviates to the left again, and now again, we can guess that it's not random deviations to the left, it's just the target is in the middle of a left turn. So we can already predict that in the next time step it will also move to the left. So we can try to model such things, and this is not, I mean, real world targets may look something like that, so the motion is truly very nonlinear, and we want to be able to learn such maneuvering. So we did the sensible thing. We replaced the linear model with some type of a neural network. Specifically, we used LSTM, and it has parameters, and now we only need to train these parameters. So, you know, just like training any RNN, we run the Kalman filter with our neural network over all the data of the trajectories. We get the predictions, we get the prediction errors, and we optimize them using a gradient descent in whichever variant.
So you've ended up with a neural network that is able to predict the trajectory of the target.
Sorry, can you repeat?
So you said after training that STM neural network, you were able to achieve a predictor for the target trajectory.
Yeah, I mean, yes. Yes, here the prediction model F, its job is to tell you what's the next state is going to be according to the current state, right? So I just replace this F with a neural network, and then you know you run this whole black box over and over again, and each time you get this estimate, which indirectly relies on this. So you get this estimate, and you know you can calculate the error in this, and that is what I optimize. Okay, because that's what I want to eventually to be able to do. I want these estimates of the states to be the best. Okay, so I optimize this to get better predictions here. Now, yeah.
In the classical setting, the Kalman filter is not a learning task. There's nothing to learn. You have a model, you have a noise.
Yeah, as I showed in the previous.
And Kalman filter, like the basic one is defined for linear problems.
Yes.
So if it's not linear, you need to extend it. This is sort of orthogonal to the learning problem. There's one thing which is learning the
This
function.
is a great question. Let's save it for later. All right. So we optimize theta, the parameters of the neural network, in order to optimize the predictions. And we already sorry, we also have the parameters of the original Kalman filter, Q and R, corresponding to the noise. And you know, the meaning might be a little changed under this modified model, and we already have an optimization of parameters, so we throw them into the optimizer as well, and now we optimize all the parameters together in order to improve the predictions of the Kalman filter. And we do that, and we get better prediction accuracy, and we were all very happy, and we started writing a paper about it. And in the paper, we noticed that indeed we have two technical contributions here, which relates to what you said. We added the neural network in order to have a non-linear prediction model. And we also took the original parameters of the Kalman filter and used optimization, supervised learning to optimize them. So when you have two different contributions, you do some ablation tests, and in one of them we just removed the neural network entirely. So when we do that, we essentially just get the original Kalman filter, the linear Kalman filter, and the only difference is that the parameters, we optimize them instead of taking the covariance, the estimated covariance matrices. And as it happens, this was better, not just better than the Kalman filter, but also better than the neural Kalman filter. Okay, so it gives us a 100 and something % of the improvement, and the neural network actually only made things worse.
Can you repeat what did you exactly do to make it better?
Yeah, so we have the original Kalman filter. We said that F and the H, the models, are defined manually, and that the parameters are set according to the covariance matrices that we estimate.
Yeah.
So the main idea in the neural Kalman filter was to take the models and learn them. And also we took the parameters, and instead of just setting them to be the sample covariance, we said, okay, these are parameters of the model, let's optimize them with respect to the ultimate objective, which is the final predictions. Okay, and by doing that, this actually, we found out that this gave us all of the improvement, and the learned model, the non-linear model that we learned, this actually only made things worse. Okay, so to your question, what's the difference between the optimized Kalman filter and the Kalman filter? It's about the parameters Q and R, whether you treat them as covariance matrices to estimate or you just optimize them. Now, this is quite surprising. First, it's surprising because the problem is very non-linear, and still the Kalman filter was better than the neural network. So this was very frustrating because my paper was about getting a better neural network, and and I tried to tweak the benchmark, and I tried to improve the neural network and the learning, and I wasn't able to improve over the Kalman filter. So I think this is very interesting, but still it's just anecdotal. I mean, maybe in other problems, maybe in other neural networks, it would work better. So this is just a point for thought. But more interestingly, I didn't know that the Kalman filter was better. I actually thought that the neural network won in the experiment. And the reason for that, the only thing that made me notice that the Kalman filter is better is that at some point I accidentally optimized the Kalman filter parameters just like the ones of the neural network. So this is the first major takeaway from this talk, that when you compare neural network to a Kalman filter, you should always make sure that you optimize the parameters of both in the same way. And you already kind of mentioned it, that it sounds quite trivial, right? Like we compare two different architectures, we need to optimize them in the same way, right? That's pretty trivial, except that if you look at the literature of nonlinear filtering, you see that virtually all the works take some kind of novel neural network and compare it to either the Kalman filter or the extended Kalman filter. And in all of them, they do not optimize the parameters of the Kalman filter in a similar way to the neural network. And there's actually a pretty good reason for that when you think about it, because we know from the original paper of Kalman in 1960 that actually estimating the covariance matrices and set the parameters to be just the covariances, this already gives us exactly the same optimal predictions of the model. I mean, it's supposed to be exactly equivalent to optimizing the matrices Q and R with respect to the final predictions. So how is it possible at all that we actually got any improvement by doing the optimization? And the answer to that is that, well, this is true. This is true under the strict, unrealistic assumptions of the Kalman filter. In the full-time lecture, I get into a toy example of a Doppler radar, and I show how even in this very simple problem, we can find like 4 different violations of the Kalman filter assumptions, and some of them are very tricky to even notice. So the bottom line is that in practice, we cannot trust the Kalman filter assumptions to hold, and then this equivalence breaks. And now, if we want to optimize the errors, we can no longer rely on just estimating the covariance and let the math do the rest for us.
The estimation is on the predicted place of the radar target. This is the estimation, or there is another estimation above?
You mean the estimation here, you mean? It's a...
In your experiments, okay, you try to estimate the correct place of the radar target. This is and in this point of view, you found that trying to estimate the Kalman filter's properties is better than replacing the whole Kalman filter, right?
I mean, I didn't replace the whole Kalman filter exactly at any point, but I found that just modifying, just learning the parameters properly, it was more beneficial than replacing the internal models.
Because there are a few work about estimating the CFAR of radar targets and
the CFAR.
The CFAR is the coverage to interference in radar targets. So another experiment that ELTA did in last year, and there is the same results. Changing the Kalman filter properties was better than.
So actually, this work is originally from 2022, and I'm not familiar with what you mentioned.
There's something a bit confusing in the whole framing. Like, it's not Kalman filter beat neural network. You're in the Kalman filter setting, and the question is like, what parts are you estimating directly, and what parts are you trying to optimize in a different way? So, like, you're always in Kalman, right? Like, isn't it more? And it's just a matter of, am I optimizing the transition functions, or whatever you call it? Am I optimizing the noise? Am I doing both?
So you can put it the way you did. It's indeed still in the framework of the Kalman filter, in the sense that I have the 2 steps, the prediction and then the update or filtering.
No, and even the form of the prediction and the update is, you could have done a predict and update in a different, like the equations, or the predict.
It's true that I could have done many things differently. I mean, if I just used the naive LSTM to do the whole prediction end to end, then in the basic form I wouldn't have the uncertainty estimation of the Kalman filter, so I would lose some of the functionality. So I did keep the Kalman filter framework and just replaced the specific models for the predictions, and also I tried the observation models. So you can say that I just switched components. But okay, so I switched components to neural networks, and I expected them to give me better results, and they didn't.
So perhaps the thing is not the Kalman filter assumptions do not hold. The Kalman filter, there's like the big framework of Kalman filter, and then there was a derivation of the particular parts for the original problem, linear, Gaussian, IID, etc., etc. And like every assumption that you remove, you can replace, but then you just might have to change the equations accordingly.
So maybe the confusing part is that here, when I get here, I already forget about all the neural parts. Now I focus on the Kalman filter itself and the original form of the Kalman filter, and I say, okay, there are the parameters, and how the hell it's possible that I replace these parameters that are supposed to be optimal and got better results? And my conclusion is that it's because the Kalman filter assumptions do not hold. Now you're right that under a different set of assumptions, I can sometimes derive a different form of the Kalman filter. For example, in the paper, we show that we have this toy Doppler radar problem. If we make it even more toy, I said there are 4 different violations of the assumptions. If we remove 3 of them, now we have only 1 violation, the nonlinear observation model. Then you can actually do the math analytically, and you can write the new equations, and you see that this is exactly what the optimized Kalman filter learned. The thing is that to do that, you must have a problem that is solvable analytically. You must notice exactly all the violations of the assumptions, and it took me, I think, a week of work to get all of them properly. And when you are sure about that, then you can do that. And we propose how to do that directly from the data without knowing all this information and without needing to overcome the assumption. We just, by learning from the data, we compensate for all the model misspecifications. Okay, so we ran a lot of experiments, a variety of experiments, so that all the reviewers are going to be happy. And I'm not getting into them. I just want to focus on one specific experiment where we took training data sets of different sizes, and we see that the optimized Kalman filter is better than the original one, and when you feed it with more data, it learns better, it gets better accuracy. But in this specific example, when we took the Kalman filter and we gave it more data, it actually deteriorated in the predictions. So it gets more data. Certainly the covariance matrices are now more accurate. The estimation of the covariance is now better, but the estimation of the covariance, as we said, it's not equivalent now to optimization of the final prediction because the assumptions do not hold. So I think this illustrates very clearly the main message here, that these problems are no longer equivalent, and you must optimize the parameters explicitly in order to solve the actual problem that you want. So this is for today. As I said, the main message is that when you compare a neural network to a Kalman filter, make sure to do this fairly with a similar optimization. And more generally, since you can't rely on the Kalman filter assumptions in the real world, more generally, when you use the Kalman filter in this setup, it's a supervised setup, and you have the x's, the true states in the data, you should just optimize the ultimate objective that you want. And if you ask how exactly to do that, then as I said, it's basically just like with RNN. You run the model and you propagate the gradient from the errors, except for a minor trick that the matrices are still covariance matrices, so we want to keep them like symmetric and positive definite. So you need to do their Cholesky parametrization in order to keep this structure. But except for that, it's all the same optimization, and if you like, we have a PyPy package that already implements it. That's on training. On inference, very nicely, unlike the neural network version, in this optimized Kalman filter, you don't need to change anything. You don't have development overhead, you don't have computational overhead, you just run exactly the same Kalman filter and just need to change the parameters according to what you learn. So I think this is it. If you have any more questions, please feel free. Yes.
Isn't the neural network able to express Kalman, the optimized Kalman filter?
So your question is that the neural network, it's supposed to, I mean, the Kalman filter is a particular case of the neural network with specific parameters.
Yes, including the optimized Kalman filter.
Yes, this is true, and still in our experiments, it didn't do better. Seems like an optimization issue, overfitting maybe, even though I tried to give it more data. I even modified the architecture of the neural network to make sure that it's indeed more easy to learn to express the linear model. And I initiated it to the linear model, and I tried everything. And yeah, these things are tricky, but maybe you will succeed better.
Did you try?
Yeah.
Did you try directly having a neural network to train a neural network that gets a state and a covariance and outputs and a measurement and outputs state covariance and measurement end to end?
I didn't try to do that. Supervise the prediction of the covariance because the right covariance is 0, right? The right, I mean, in the data we have the x's, which are the supervision of the location, and when you train the model to make the best predictions.
The covariance is sort of a nuisance parameter. I don't really care about it, but it will affect your next prediction.
Interesting. The answer that we didn't write.
Because it seems like Kalman filter's form depends on many, it looks the way it looks because it assumes linearity and many stuff. And you say you care about the settings where this assumption is incorrect. So it might be the case that it's sort of trying to force a marriage between two components, one that is capable of dealing with arbitrary stuff like neural networks, and the Kalman filter that's very weak.
So you bring up very interesting and good ideas. I think this is kind of orthogonal to the main message of the paper because there are other things we could do with neural networks. Specifically, your approach is kind of the DeepMind approach of like we have data, let's just build an end-to-end model that learns how to solve the problem. And I think that the lesson we learned here is that the more we went farther from the Kalman filter, we actually got worse results, where we restricted the model to be closer to the Kalman filter and only tuned the parameters to compensate for the issues. Then we got the best results. And I'm familiar with other works that also, when they went on to the real world, suddenly they actually, after all the optimization and everything, they got worse results than the original Kalman filter. So it doesn't, I mean, maybe the whole end-to-end approach would work, but anyway, this does not contradict the fact that, okay, when you do that, you should compare it to a Kalman filter whose parameters are optimized. Any more questions? All right, thank you very much.